Hello everyone, and welcome to the Waveshare ESP32 Arduino Getting Started tutorial. Today, we will learn about SPI communication. Compared to I2C, SPI typically offers higher transfer speeds and is therefore widely used in scenarios that require fast data exchange. For example, TF card modules, displays, and memory chips. Let's get started. SPI stands for Serial Peripheral Interface. It is a high-speed, full-duplex, synchronous serial communication protocol. SPI uses a master-slave architecture for communication. Master, usually a microcontroller such as the ESP32, responsible for initiating communication and generating the clock. Slave, usually various peripherals such as memory or displays. The slave responds to the master's requests. Standard SPI communication relies on 4 core signal lines, SCK, the serial clock line. The master generates a clock signal to synchronize the timing of all data transfers. MOSI, the master out, slave in line. The master sends data to the slave through this line. MISO, the master in, slave out line. The slave sends data to the master through this line. SS, the slave select line, also called chip select. When the master connects to multiple slaves, it selects the target slave by pulling its SS line low. Because MOSI and MISO are 2 separate lines, data can flow in both directions simultaneously. This is what we call full duplex. One additional note, you may see updated terminology for SPI in newer technical documentation. We list the old and new terms here to help you read the latest documentation. The main change is replacing master-slave with controller peripheral. The ESP32 chip typically contains multiple SPI controllers. Take the ESP32S3 for example. SPI0 and SPI1 are mainly used to access flash and PSRAM. GPSPI2 and GPSPI3 are general-purpose SPI controllers that are freely usable. In the Arduino environment, we use the SPI.h library to access these functions. Also, ESP32's SPI pins are very flexible. Through the GPIO matrix, SPI functions can be routed to most GPIO pins. Now, let's get hands-on. This example demonstrates how to drive an OLED display using the SPI interface. Components needed: 1 ESP32 board, 1 SPI interface module, 1 breadboard, a few jumper wires. This OLED module supports both I2C and SPI protocols. You can switch modes via the BS1 and BS2 pads on the back of the module. As you can see, both are currently soldered to the 0 position, which means SPI mode is enabled. Connect the circuit according to the wiring diagram on the screen. Now let's look at the code. You can find a link to the tutorial document containing this example code in the video description. This example depends on the Adafruit SSD 1327 library. We have already installed this library in the I2C lesson. If you haven't installed it yet, search for it in the Arduino IDE Library Manager and install it, then install all dependencies as prompted. The focus of this example is not the display itself, but learning how to correctly configure the library to use the specified pins. Generally, libraries that drive SPI displays accept an SPI object that uses default pins. Let's initialize the SPI object with our custom pins. First, at the top of the code, define the pins we need. You might be wondering, standard SPI uses 4 wires. Why does this code have no MISO? And why is there an extra DC pin? This is a typical situation when using SPI to drive a display. Why is there no MISO? Because this OLED display is an output-only device. The ESP32 only sends data to it and never needs to read anything back. In this unidirectional communication scenario, the MISO line can be omitted. What is the DC pin? DC stands for Data Command. It is an extra control line found on many display modules. It tells the display whether the data being sent next on MOSI is pixel data to be shown on the screen or a command to control the screen. Next, find this line. Here we create a display object. By passing the SPI parameter, we tell the library to use the hardware SPI interface to drive the display. Then, inside the setup function, before calling display.begin, we need to initialize the SPI bus and assign custom pins. The SPI.begin function configures pins in the order SCK, MISO, MOSI, CS. Because we are not using MISO, we pass -1 in the second parameter position, indicating that this pin is ignored. After these 2 configuration steps, the rest of the drawing and display work is all handled by the graphics library. After uploading the code, the OLED screen will light up and display Hello World and SPI test. We know that a single SPI bus can connect multiple slave devices via chip select lines. However, the master can still only communicate with one device at a time. If you need to simultaneously communicate with multiple devices at high speed, ESP32's multiple SPI controllers become very useful. In Arduino, we can achieve this using the SPIClass object. For example, create an independent object for the second SPI controller. Then, in the setup function, initialize it and assign pins just like the default SPI object. This gives you 2 independent SPI channels that you can control separately. Well, that's it for this lesson. Let's quickly recap. We learned the core concepts of the SPI protocol, including its master-slave architecture and the 4 core signal lines. We practiced driving an OLED display with custom pins and learned about additional control lines like DC. Finally, we saw how to use SPIClass to enable multiple SPI buses on the ESP32. In the next lesson, we will learn how to connect the ESP32 to a network, the basics of Wi-Fi. Thanks for watching, and see you next time.